Welcome to ZKast, everyone. I'm Kerravala from ZK Research, and today we're going to be unpacking how AI data centers are evolving and the technology that's enabling them. While I specifically going to be looking at networking, and while networking makes up several critical components, this discussion will focus on the network's role in creating what NVIDIA CEO Jensen Huang often refers to as the new unit of compute. We're going to dig into new optics, the ability to scale across AI data centers, partnerships, and the need to be open, as well as how to accelerate adoption. And so today, joining me will be Bob Laliberte, Principal Analyst at theCUBE, and as my co-host, as well as a special guest, Gilad Shainer, SVP of Networking for NVIDIA. So welcome, gentlemen. Bob, how you doing? And a little intro on yourself.
Doing great, Zeus. Thanks so much to have me here. Really looking forward to this conversation. And Gilad, thanks for joining us as well.
Yeah, and Gilad, Bob's on all the time, so we don't really need much of an intro to him. But you talk about your role at NVIDIA, networking NVIDIA, really interesting set of products there. So what's your role and what do you do there?
Thank you for inviting me and happy to be here. I've joined Mellanox many years ago and started actually as a ASIC designer and was involved in the design of the first InfiniBand adapter that was created. Later on, I participated in multiple developments, both hardware, infrastructure, software, and then a few years back with the acquisition of Mellanox, joined NVIDIA, and focusing on building the infrastructure that actually create the AI data centers. Now you mentioned networking, and networking is so much, it's like a large last century word to describe what we do. It used to be networking because essentially in the past, the networking devices or their mission was to move data from one side to another side. Mm-hmm. Today, it's not really networking anymore. It's actually a computing infrastructure. It's something that takes takes those compute ASICs and help to form a supercomputer. So it's not just moving data, it participates in the computing activities. It's actually drive elements that new and were not being part of the infrastructure before. So we don't really call it networking, but it's actually a computing infrastructure, and this is what we're doing.
Yeah, and well, you certainly got networking in your blood, or compute infrastructure, if you want to refer to it that way. Before we get into some of the networking changes, though, I'm curious about just the overall state of AI. And as AI becomes mainstream, and we evolve, everyone's going to have to evolve their data centers. Can you talk about some of the limitations of networking and why it needs to evolve in this way?
Yeah. So when we talk about AI, we are talking about distributed computing workloads, and that's something different than a traditional cloud workloads, for example. In traditional cloud workloads, most of the workloads are actually a single core workload, a single CPU workload, single server workload. And therefore, those the hyperscale cloud systems are systems that packs a lot of servers and actually have a network that its network mission is to connect the end users to the servers in order for the servers to run that mission or to run the workload. When we talk about AI and we talk about distributed computing, it's a multi-server workload. And it's not just few servers, we can talk about hundreds of thousands of servers, of compute engines that need to work as a single unit. And therefore, building an AI data center is actually building a supercomputer. And a supercomputing mission is to combine multiple compute ASICs and make them work as a single entity, as a single unit. And therefore, an AI supercomputer is being designed completely different than a traditional supercomputer. And actually, it requires multiple infrastructures that surrounding those computing ASICs in order to build that supercomputer. And we talk about a scale-up computing infrastructure, that its mission is to connect those compute ASICs and to form one GPU. Right? That's why we talk about a rack scale GPU, right? It's like the rack is a single GPU, and it's all because of the scale up infrastructure. And then when you form that single rack scale GPU, you need to connect multiple of those together, and they all need to work in a very symmetrical way, and they need to be completely synchronized between themselves, because essentially it's running one job across everything. And this is where you bring a scale out infrastructure that its mission is different, is to take those racks and actually create a large data center or one unit of computing. And then because of physical and power limitations, you may need to connect multiple data centers together to form a gigawatt, a gigascale supercomputer. And this is where another infrastructure being created, and it's scale across. So it's different elements that actually do that. And you need to have an access network and so forth. So in a traditional data center, single server workload, there is actually one network connects to the servers, and that's how it's built. It's kind of closer to a server farm. In AI data center, it's building a supercomputer. And that supercomputer can be actually located in multiple places, but it needs to be work or behave like a single unit.
Yeah, and so it's interesting because you touched on, I think some things where NVIDIA has really helped is helping people scale within the rack, right? Scale up, scale out across the data center, and then you introduce this concept of scale across. And can you talk about a customer scenario where they would have to, where scale across is really their only viable path?
Yeah, definitely. So when you build a data center, you have two given elements. One of them is how much power you can utilize in that location. And sometimes it's also a physical constraint. What's the space that you have? And those two elements will determine how much compute you can bring or build in that data center, how many GPUs you can build, or what's the size of an AI supercomputer. Now, with the growth in the requirements from both AI training and inferencing, we see the scale that goes beyond what you can build in what you can put in a single building, what you can build in a single location. Which means is that in order to scale your workload, you will need actually to connect multiple buildings together, multiple sites together. Those sites may be far away. And it could be buildings within a campus, it could be between campuses, it could be between cities, it could be between countries. Mm-hmm. But you do need to run across everything, because you need the combined computing capabilities of all those data centers to support a single workload. And in order to do that, we design a new infrastructure, which is scale across, that actually makes the data center work as a single unit. You can think also about other cases. There is entity that would like to use, for example, renewable energy, and therefore they're going to build data center where they can have renewable energy. So that's another example where you're going to have data centers in remote locations, but you do need them to work as a single unit. And as we scale and the demands from the workloads increases, you will see more and more entities and more of our customers actually leveraging scale across and leverage the Spectrum XGS Ethernet for that scale across infrastructure to actually form a data center to data center connectivity and larger mega scale AI factories.
Gilad, that makes so much sense. And obviously adding that now instead of just scaling up and scaling out, now that concept of that ability to scale across, especially for organizations looking to take advantage of sustainable energy sources, right? Renewable energy sources, which may not be that close to each other. So having that is certainly going to add another dimension. And it also, it's great to bring out now for organizations who are starting to scale their environments to be thinking about that ahead of time and where they want to be, and give them options for where their AI data centers can go. And obviously, like I said, a lot of this driven by energy. So I wanted to touch upon another area that's rapidly evolving, and that's around the co-packaged optics or CPO. How does that CPO perspective, how does that change the economics and energy profile versus today's pluggables, especially in those large GPU fabrics?
Yeah. So one of the things that you are aiming to do, or you want to do when you design a data center, is to build it in the most efficient way. So you want to improve its power efficiency. You want to improve its energy efficiency. The more power that you can save, the more computing that you can bring in. And therefore, you want to leverage all of the technologies that enable you to reduce power consumption. One example, and before touching co-packaged optics, is usage of copper. Mm-hmm. Copper is zero power. So as much as you use copper, as long as you can use copper, you can save power, and you want to use copper as much as you can. And what we are focusing in the scale up infrastructure in NVLink is to pack as much compute as we can inside the rack, so we can focus the scale up or NVLink infrastructure on copper. And that's why, for example, we building our computing in racks with liquid cooling, so we can increase the compute density. We're working with our ecosystems and our system design team to be able to make the rack more efficient and actually increase the compute density, and that increase the capabilities of NVLink and so forth. So this is one area of focusing on utilizing copper, because it does gives you the best power performance that you can think about. Now, once you maximize the rack and maximize the scale up infrastructure, then you need to go to scale out. And scale out need to drive longer distances. And this is where copper cannot be used, and essentially using optics. Now, in the traditional data centers, most of the work was inside a server. So the connectivity between the rack was not that much. So there is optical connections, but that optical connections that consume more power than copper, obviously, was not a big factor. When we're talking about AI, there is actually a lot of bandwidth that needs to be driven in the scale-out infrastructure. And as GPUs progress from generation to generation, and the infrastructure progress or advance from generation to generation, there is more bandwidth that is needed on a scale-out. The amount of power that is consumed by the optical connections in the scale-out infrastructure can reach almost 10% of compute, which actually it's a big number. So if we can save power on that scale-out infrastructure, we can increase the compute capability of that data center. And in order to do that, we've introducing co-packaged optics. And we announced the Spectrum-X Ethernet co-packaged optics, and we announced the Quantum-X InfiniBand co-packaged optics. And the motivation or the idea is very simple. When you have an optical network, you have switches connected to transceivers, and the transceivers connect to fiber that goes between them. There is a dense distance between the transceiver and the switch, for example. So you need to invest power in order to transition an optical signal to electric signal and go through multiple transitions of cages and PCBs and packages and so forth until it gets to the switch. This is where you can optimize. So with Spectrum-X Ethernet photonics, for example, with co-packaged optics, we've moved the optical engine and put it in the package with the switch, reduce the distances, reduce the power that you need to use for driving the signal. And with that, we are able to reduce the power consumption of the scale-out optical infrastructure by 3.5x. So for the same ISO power of the scale-out network, now you can actually connect 3x more GPUs. It's a huge number. Now, there is other great side effects, quote unquote, because the design that we have done with an ecosystem of partners, and there is a huge amount of innovations and work with multiple partners, TSMCs on packaging and other vendors on laser sources and optical arrays and so forth. First, we created an optical engine that is very efficient. Unlike traditional attempts out there that were focusing on MZM designs, which results in a large optical engines that will limit the radix of the switch, we design an optical engine which is very, very small. It's micro-ring modulator design. It's very small, so it can actually support large radix switches, which are important for the scale-out infrastructure. We work with TSMC on packaging, for example. We work with partners around laser sources, and working with them, we are able to reduce the number of lasers compared to a traditional aspect by 4x. So it's power reduction, it's reductions in number of components that you need in order to build a data center. So the resiliency is 10x improved. The power consumption is 3.5x less in that sense. And this is another aspect of improving performance or power performance per watt, and be able to bring more computing into data centers and to make them more efficient.
Awesome. That was great, Gilad. Thanks so much for that. And it certainly highlights a significant number of benefits going with those co-packaged optics. So hopefully everyone who's listening is going to be able to make sure they're starting to factor that in as they start to scale out their environments as well.
Yeah, Gilad, and you use the two terms. You talk about power and energy, and I find often in this industry, people conflate those two terms, and there is a difference in power efficiency and energy efficiency. And so, can you talk about how you define the differences and what KPIs operators should be prioritizing between those two?
Yeah, well, first, both are important. Okay, let's start from that side. Power efficiency is measured by performance per watt. Okay, so you want to improve the performance per the power that you consume. And for example, co-packaged optics is a technology that enables you to improve performance per watt. Using copper for our NVLink scale-up, it's improving performance per watt. It's improving the power efficiency of the system. Liquid cooling does the same thing, right? So those are examples. Now, when we talk about energy efficiency, we're talking about what is the total energy we need to invest in order to complete the task. When you're running training, when you're running inferencing, it takes time. It can take days, it can take weeks. The question is, what is the energy that you need to invest in order to complete your task? Your data center can be very power efficient, but it may take that data center twice the time to run a job, and therefore it will have very poor energy efficiency. Okay, you want to improve on both. So, for example, the reason that we created Spectrum-X Ethernet is because off-the-shelf Ethernet infrastructures that existed were not built for distributed computing workloads. Okay, they were built for traditional clouds, single server workloads. They were built or designed for heavy virtualized enterprise. They were designed for service providers. They were not designed for distributed computing. So if you were using an off-the-shelf Ethernet to run an AI workload, that could easily take you 40%, 50%, 60% more time to complete the job. And that means that your data center energy efficiency will be very poor. With Spectrum-X Ethernet, that actually is designed to support distributed computing. It's designed to eliminate jitter. It's designed to have very highly effective bandwidth. It's designed to make sure that all of the computing engines simultaneously work and get data at the same time. That can save a lot of time in running the workloads. So we demonstrate, for example, reductions almost 40% of running training when you're using Spectrum-X Ethernet versus using off-the-shelf Ethernet. And with Spectrum-X Ethernet, it takes you less time to run a job. It takes you less time to run training or running inferencing, which means we're optimizing the energy. So both are important. One is performance per watt. The second one is energy per job. And we want to optimize them both.
Okay, thanks for that. That makes sense.
Yeah. Gilad, I wanted to touch base on something else. There's been some chatter recently about proprietary AI fabrics and so forth. I'm wondering if you could highlight how NVIDIA supports multi-vendor interoperability in practice and maybe discuss any of the deployments that you have today.
Yeah, well, let's look on that. So first, when we look on the scale-out infrastructure, we have Quantum-X InfiniBand and Spectrum-X Ethernet. Both of them are fully industry standard. Quantum-X is built according to the InfiniBand specification that are managed by the IBTA consortium. And then Spectrum-X Ethernet, it's Ethernet. So it's a full Ethernet connectivity. It's interoperable with any Ethernet device that exists. So that's from an interface perspective. Now, even the software that runs on top of that, the operating system that runs on top of that scale-out infrastructure, it's also open source. So you can actually run the Sonic open source operating system on top of the Spectrum-X Ethernet infrastructure. And it's important for us, because with that open source capabilities, it means that our customers can innovate on top of that. They can bring their secret sauce into the software that runs on top of our infrastructure and customize it to the workloads that they want to run. When we look on scale-up infrastructure, we announced NVLink Fusion. Okay, so with NVLink Fusion connects with an industry standard interfaces to any accelerator, to any CPU that exists. And therefore, any accelerator or any CPU can connect to any scale-up infrastructure, including NVLink Fusion. And with that, we're enabling people actually to utilize the best infrastructure for their usage. Okay, so first, Spectrum-X is Ethernet and Quantum-X is InfiniBand. Both are industry standards and have open source running on top of that. NVLink, which is an amazing infrastructure, and it's not easy to build a scale-up infrastructure because it needs to support huge amount of bandwidth and load and store operations and take those GPU ASICs and make them one and very low latency and high message rate. There is so much innovation that needs to be brought into a scale-up infrastructure. And then with NVLink Fusion, we're actually enabling anyone to use that amazing scale-up, and they can bring their own accelerator, their own CPU, their own combination of accelerator and CPU. So the interfaces are standard. There's a lot of open source software that runs on top of that, and we enabling our partners and customers to completely innovate on every aspect of what we build.
Yeah,
I think that,
I,
sorry, go ahead.
I think, yeah, no, I think one of the big proof points though for the openness of what you're doing is the ecosystem that you have around you, and specifically, can you talk about that? But specifically around Cisco and the partnership there. I know, when people think of networking, Cisco's got more domain knowledge than maybe anybody in networking has ever had, and that's become a very important partner for you. So, can you talk about that? The ecosystem approach, but then also the relationship with Cisco and how you're leveraging their networking and software to expand the reach and adoption of what NVIDIA is doing.
Yeah. Well, we love the ecosystem. We love the ecosystem. Working with the ecosystem enable us to run very, very fast. Okay, AI is being progressed very, very quickly. If you see the progress of technology, you see the scale of the data centers, and working with the ecosystem enable you to actually run very, very quickly and progress very quickly. Cisco is a great partner. Cisco invested so many years in building infrastructure for the enterprise, and they have great software capabilities that they've built to support enterprise clients. And as we see that AI is going to enterprise, the combination of NVIDIA and Cisco is like match made in heaven. Okay, if I'm going that path, by working with Cisco and bringing our Spectrum-X Ethernet infrastructure into Cisco can leverage and offer the performance of Spectrum-X Ethernet for enterprise AI on one side. On the other side, they're running their entire enterprise software on top of it. So enterprise customers can continue to use the same Cisco software, the same enterprise capabilities of Cisco they are used to and they enjoy. And now it's actually accelerated with the Spectrum-X Ethernet underneath for the AI enterprise data centers. So it's a great partnership. It's Cisco bring their enterprise expertise, we bringing the Spectrum-X performance, and together we're building an amazing solution for the enterprise AI.
Gilad, I just wanted to go back to something that we had talked about earlier. You had mentioned the scale across now being available. If I'm a customer and I want to get started, what's the most pragmatic path for them to do? Is there reference architectures they should be looking at? Is this something that they have to design from the get-go, or can it be integrated into existing locations that they have in order to scale across to a new one?
Yeah, so first, the way that we design things is that we design a single unit. Okay, the unit of computing today is the data center, right? It used to be a CPU, it used to be a server. Now in the world of AI, the unit is a data center, and therefore we design the data center. And when we design a data center, we design it in the best way that we think that we will want to consume it ourselves, okay? The idea is that we're building a data center for our own usage, and that's why you want to build the best thing you can build. And after we do that, we offer that as a reference architecture. And our customers can take the entire design. Our customer can take pieces of that design. So they can take the GPU and they can take some other infrastructure. They can take our NVLink Fusion and put their own accelerator and so forth. They can take pieces of that if they want to and combine it with other. So there is all the options that exist here on the table. Now, scale across is, as you mentioned, it's a new infrastructure. And it's also part of that reference architecture that we have created. And if you want to leverage that reference architecture and enjoy the capabilities of Spectrum XGX Ethernet, then you can take the reference architecture and actually you will be able to enjoy from the same performance level that we're enjoying. Now, Spectrum XGX Ethernet connects remote data centers together. So it is supported by the variety of long reach options that exist. If you have built a dark fiber connections between remote data centers, you can have the Spectrum X Ethernet on both sides. Spectrum XGS Ethernet runs on top of that infrastructure with the new algorithms for the long reach congestion control and long reach adaptive routing and distribution. And you can use that. If you have a DWDM infrastructure that has multiple devices in between, you can also have the Spectrum XGS on the endpoints on both sides, and that will run across a different or DWDM infrastructure. So you can use it on existing infrastructure that you have, you can use it on a new infrastructure that you build, and it's gonna work and optimize itself according to the distance and according to the medium that exists between those remote data centers.
Excellent. Yeah, that sounds great. I'm really looking forward to hearing about from the, some of the early adopters, and not only how they're doing it, how far they're going, things like that, especially if they're leveraging the DWDM infrastructure. Cool. Thank you.
Yeah, we did announce CoreWeave, by the way, is the first customer of us that is going to use Spectrum XGS, and there is many others that we'll announce when it's time.
Yeah. No, and thanks for that, Gilad. I think what's interesting here is that we've seen AI really redefine almost every part of the IT stack, right? And I think that we're just starting to see the evolution of the network now, and it's great to see the innovation that NVIDIA has done. So I think that's probably a good place to wrap up. We talked about co-packaged optics, the data center and scale across, then what the whole definition of the new unit of compute, as well as some partnerships and openness. And so, Gilad, is there anything else you want to add?
No, first, thank you for the time today. It was really an interesting discussion. The cadence of innovation is fast. Okay, when you look ahead, we're an annual cadence of technology innovation. Every year there is a new infrastructure being created, a new data centers that is being built. So it will be great to talk with you and continue discussing new innovations. And I hope that we'll do it soon, because with the cadence of innovation, tomorrow there's going to be new device, new infrastructure that will be created.
Yeah, well, you can already, scale up, scale out, and scale across. You got nowhere else to scale now.
Oh, we'll see.
Yeah, I guess scale down, something like that. So, all right, Gilad, really appreciate your time. Bob, you as well. Thanks for joining me today. I think those were some great insights on how AI is evolving data centers and networking. And I'll also include, if there's a link that you have to those blueprints, I can include them in the YouTube description below. So on behalf of Gilad Shainer from NVIDIA, Bob Laliberte from theCUBE Research, I'm Zeus Kerravala from ZK Research, and thanks for watching. Give us a like and also hit that subscribe button. I'll see you next time on my next episode of ZKast.